Okay, good morning, and this is the last class of the catalyst stability. Okay. 210 5633, and today is the 29th of April 2021 at around 8:40. Today we will continue and concluding the student lecture, and uh, today there will be more than 20 students presenting, and please keep your presentation within the time. You have 7 minutes. You will be notified 3 minutes before uh, the the times limit, and 1 minute before the real deadline. The moderator will tell you. So we will start at 8:45. Parthenoa, please share your screen and be prepared. And we have two moderators, Natanon and Natapat, who will be helping us during our this talk. And the referee, please prepare your evaluation sheet. And after everything is done, please upload your sheet to the course view. Parthenoa, please share your screen. The first speaker. Okay, and we will start in around 3 minutes. Natapat and Natanon, be prepared. Okay.
Okay, Panchanok, please start your presentation.
Thank you. Good morning. My name is Panchanok Mungchan. Today we will talk about regeneration of catalyst deactivated by cold deposition. Topic to be discussed include with introduction, regeneration using oxidation, gasification, hydrogenation respectively, and the last is conclusion and research direction. Let's start with the first topic, introduction. The catalytic deactivation can be classified into 6 major types. We will focus on coke deposition. Possible effect of fouring by coke on the functioning of a supported metal catalyst are shown in the figure 1. Carbon may block acid of reactant of metal surface side. Totally encapsulate a metal particle, plug this pore and crossing the disintegration of catalytic pellet and plugging of reactor void. Firstly, Regeneration using oxidation can be typically represented by the following reaction. Coke oxidation is an exothermic process which stream carbon dioxide or carbon monoxide as the main product. To regenerate coke catalyst with air combustion is often the preferred and most practical route. However, high exothermicity can easily cause overheating, leading to dealumination, metal sintering, and catalytic degradation. Lu and author investigate the regeneration cycle stability of nickel alumina catalyst for toluene cracking. The cracking was followed by air combustion. The cycle performance is shown in the figure 2. The catalytic activity was stable from the first until the third cycle, but then decreased in the fourth cycle. Despite ozone and oxynitride are also potential and cheap oxidation agents able to remove coke at low temperatures, which is consistent with the research of Ivanov and Kopovets. Next is the regeneration using gasification. Carbon dioxide can act as a mild oxidizing agent with reacting with coke, as shown in the equation 5. Regeneration of coke catalyst via carbon dioxide gasification can reduce CO2 to CO, beneficial to the carbon footprint. Su and author conduct comparative tests to regenerate coke, nickel alumina catalyst used in reforming of bio oil with carbon dioxide, steam, and air, respectively. They found that carbon dioxide was the best choice. However, the catalyst regenerate with carbon dioxide gasification at 700 Celsius show lower activity and stability than the first catalyst. Moreover, the activity and stability of regenerate catalyst gradually decrease with increasing regeneration cycle in the figure 3. Moreover, steam as gasifying agent in regeneration process can also mitigate the accumulation of carbon dioxide and produce gas. However, when the steam is used to remove coke deposit on catalyst at high temperature, it can destroy the stock of catalyst and cause permanent catalyst deactivation. Hence, the catalyst must have an excellent hydrothermal stability. The shape of coke gasification with steam can be described using equation 6, and they consistent with the research of Tyan and authors. Later, regeneration using hydrogenation. The coke removal reaction with hydrogen can be described with equation 7. Walker and others found that the relative coke removal rate at 800 Celsius was in the order of oxygen, steam, carbon dioxide, and hydrogen, which means that hydrogen is relatively inactive, and coke regeneration with hydrogen is a time or energy consumption process. The characteristic and challenge of this regeneration method are summarized in the table. Although the coke deposit on catalyst can be removed via oxidation, gasification, and hydrogenation, air is typically used in industrial process to regenerate the activated catalyst because moderate regeneration temperature can be applied. Ozone and oxynitride can lower to regenerate temperature, but they are harmful gas and their emissions are strictly controlled. Coke gasification with carbon dioxide or steam can transfer the low-value coke into value-add syngas and simultaneously reduce the carbon dioxide emissions. However, coke gasification is a highly endothermic reaction which needs high temperature that may destroy the catalyst structure. Coke can also be removed with hydrogen at high temperature or pressure. It is worth to further study and develop optimal method for coke removal. Future research might include one intrinsic regeneration kinetic that consider the catalytic active site, two, the synthesis of catalyst with excellent thermal and hydrothermal stability, and cold removal with carbon dioxide and water stream gasification at high temperature. 3. Addition to lower the generation temperature. And 4. Catalytic process with partial regeneration that not only increase carbon utilization but also improve product selectivity. Therefore, improving coking resistance and increasing coke removing activity of catalysts remain challenge to be solved by both academia and industry. Thank you for your attention.
Okay, thank you. Next is Pakawat. Please prepare your presentation. And the presentation will start in 1 minute.
Okay, are you hear me?
Yeah. Okay, you can start.
Good morning, everyone. My name is Hua Seng Kim. Today, I would like to present about catalyst deactivation. The topic is study coke formation during the propane dehydrogenation. Okay, my presentation will be in 3 parts: introduction, lecture review, and conclusion. Okay. Introduction: propane dehydrogenation is favorable alternative method for propane production. In recent years, propane is one of the most important raw material in the petrochemical industry. It is the basic building block for variety, commodity, and specialty chemicals. But one major problem for propane dehydrogenation is coke formation on the catalyst. Okay. Platinum-based catalysts have been successfully used in some commercial propane dehydrogenation process. However, these catalysts are prone to fast deactivation by coke formation under the high temperature reaction condition. Therefore, a catalyst has to be developed with high resistance to coke. The analysis of coke becomes essential. Today, I have selected 2 examples for the research paper. Paper 1, the topic is coke formation on platinum tin on alumina support catalyst for propane dehydrogenation. Okay. Catalytic performance. From the picture, conversion of propane decreased from 71.1% to 16.6% after reaction for 4 hours. The decrease of conversion can be attributed to the catalyst deactivation by coke formation. As coke can cover active site and subsequently reduce the available active sites of the reaction. And next, for using FTIR and Raman spectrum, the coke from the catalyst can be divided into 3 types: precapite, aliphatic, and aromatic. Next, the TG analysis and pyrolysis TC give amounts of coke in show this the picture in this slide. Okay. And the institute did study the quantity of aromatic coke increased with elevated temperature. And the amount of propene and aliphatic coke decreased with elevated temperature. Okay. Okay, conclusion. The institutive study shows that aliphatic coke can be transformed into aromatic coke under elevated temperature. And this transformation is associated with dehydrogenation reactions. The results obtained in this work are helpful for the rational design of robust platinum-based catalyst for propane dehydrogenation against deactivation by coke. The proposed analysis procedure of coke is pretty of should be used to study other reaction system with coke deposition. Next paper, the topic is effect to boron promotion on coke formation during propane dehydrogenation over platinum alumina catalyst. Okay. Effect of boron promotion over the catalyst. Promotion boron does improve the performance of the catalyst. The activity and carbon formation are affected by boron loading. The figure 1 is shown that addition of boron to the catalyst has larger effect on amounts of carbon than the propylene used. Okay, the light picture, the performance of platinum boron gamma alumina support catalyst is in comparison to reference the platinum alumina catalyst. Okay, it shows the figure 2. Boron promotion clearly enhance both stability and selectivity of platinum catalyst. Okay. The initial activity both catalysts are similar, comparable TOS, suggesting that boron are not significant influence the activity of site are propane dehydrogenation. Okay. Slide TPO profile. It show for platinum catalyst show is dominant P 505 degrees Celsius and the second P 630 degrees Celsius. Promotion with boron dramatically modify TPO profile. Okay. Enzyme form the near to complete eliminate of carbon removed in 250 to 550 degrees Celsius region and reaction the amounts of carbon removed at higher temperature. Conclusion, the promotion of platinum gamma alumina catalyst with optimum amount of boron reduced carbon deposition and enhance the propane selectivity during propane dehydrogenation, leading to an increase in productivity. Specialty promotion with 1% base boron increase the amount of carbon T4 and increase the propylene activity from 90 to 98% over the experiment. Thank you for your attention.
Okay, thank you, Pakawat. Next is Rachanon. Rachanon, please prepare your presentation. And the presentation will start in 1 minute. Okay, Rachanon, you can start.
Hello everyone, I'm Rachanon Medeshan. I will talk about the podium catalyst in catalytic methane oxidation. There are three contents: introduction, literature review, result, and discussion. First of all, is the introduction. I will talk about the background and inspiration. The concentration of methane in the atmosphere is currently around 2.5 times greater than pre-industrial levels, and is increasing steadily. This rise has important implications for climate change. Estimates of methane emission are subject to a high degree of uncertainty, but the most recent comprehensive estimates suggest that annual global methane emission are around 570 million tons. This includes emission from natural sources and originate from human activity. A ton of methane emit damage the atmosphere equal to 28 tons of carbon dioxide, so methane decomposition method was necessary. Next is literature review. What is the catalytic methane oxidation? Catalytic oxidation is the process that oxidize the compound using catalyst. The oxidation of methane over an oxidation catalyst is described by the equation below. To achieve high methane conversion, palladium-based catalysts are generally considered to be most active to oxidize methane, and other short-chain hydrocarbons shown in Figure 3. Other experiment was comparing three different types of catalysts. Conventional palladium alumina gave methane conversion for about 87% and stable at high temperature. There are two ways of palladium deactivation: water sintering and sulfur poisoning, which considerably ruin the catalysis process. With steam-induced sintering, the catalyst would melt and the active site would sinter. Rahman Golmi focused on the inhibition and deactivation effect of water, especially at relatively low temperature, represent of methane oxidation over palladium catalyst in a natural gas engine. Kingston studied that the behavior of palladium aluminum only in the presence of 5 ppm sulfur in the gas phase. The conversion decreased to 10% because of sulfation. To overcome the poisoning effect, very higher temperature required and is up to 800 degrees, which is incredibly high for the process. Palladium silicium oxide catalyst was introduced to get rid of the drawback of palladium catalyst in methane oxidation. Liu studied that the effect of high temperature pretreatment on the transformation of palladium and silicium oxide species. This result revealed that the silicium coated palladium nanoparticles were highly dispersed on mesoporous alumina, resulting in a 90% methane conversion in 392 degrees Celsius. The catalyst pretreatment at 600 degrees Celsius was found to possess the best sintering resistance for methane oxidation, and the final conversion temperature was as low as 420 degrees Celsius. The result from Alexandra about catalytic performance for methane oxidation in dry and wet atmosphere are shown in Figure 10. The addition of water into the reaction feed causes an increase in onset of methane oxidation accordingly to the inhibition effect of water on the reaction. This might be related to the different palladium oxide and palladium dynamic observed in the presence of water. So they can really protect the palladium from sintering, result in complete conversion of methane. Violeta studied the effect of sulfur on palladium ceriac catalyst in methane oxidation. The results show that the ceriac gave the huge support on the reaction. Ceriac protected palladium by forming itself cerium sulfate. The methane conversion goes up to 100% even when 10 ppm of sulfur are presented. The reaction reached 80% conversion at 350 degrees Celsius, so show it performance at low temperature. Okay, here's the result and discussion. Also the future trend. The palladium catalyst shows performance in methane conversion, but gave some of its drawback. The reaction run at 450 degrees Celsius and give at least 80% conversion. The conversion is high, it is up to 87%, which is enough for cleaning methane from exhaust gas. But the drawback is the catalyst deactivation. When the sintering takes place, the catalyst starts to sintering. The conversion decreased from 87% to 20% caused by palladium oxide and palladium bimetallic domain formation on supports. Moreover, the sulfur in natural gas versus the catalyst also. Sulfur percent the catalyst made conversion drop from 87% to 10% because of palladium sulfate and aluminum surface formation. To overcome this drawback, palladium cerium oxide are introduced. This catalyst shows performance in methane conversion. The reaction can run at relatively low temperature at 350 to 450 degrees Celsius and enable it 80% conversion. The conversion is high enough and the drawback in the catalyst reaction is overcome. When the steam takes place, the catalyst does not start to sintering. The conversion maintains close to 10%, 100% until 1000 Kelvin, at which polymer oxide, polymer bimetallic domain formation are suppressed. Moreover, the sulfur in natural gas no longer present catalyst. Ceria help the catalyst by forming cerium sulfate and prevent the formation of palladium sulfate. The future trend and possibility to protect the catalyst from sintering and contact with steam and sulfur. Core shell ceria and palladium catalysis were to focus. The core shell protect the palladium steam from sintering, which is key role by making a longer lifetime catalyst. And the sulfur attack the palladium because it at 3 electron orbital and form pi bond, making thin film in membrane consuming. We prevent this problem by absorb all methane and oxygen and deny the plotting of sulfur. Another area is microreactor, which is set in internal combustion engine vehicles. This can reduce the methane emission a lot. Thank you for your kind attention.
Okay, thank you, Rashana. And the next is Waramit. Waramit, please prepare your presentation. And the presentation will start in 2 minutes.
Hello everyone. Today I will present about the activation of cobalt in catalytic.
Waramit, please wait. You can start and in 1 minute.
Okay. Sorry. Is Hello everyone and Professor. Today I will present about the activation of cobalt in catalytic Fischer-Tropsch synthesis. I will talk the content that objective, introduction, literature review, and research direction. Objective for this research: the first, to study the deactivation of cobalt catalyst. Then the second, to study factor of affecting the activation of cobalt catalyst. And the last, to develop catalyst and Fischer-Tropsch process. Introduction. Fischer-Tropsch synthesis converts synthesis gas or synthesis gas into a wide range of hydrocarbon that can be refined into drop-in commercial products like diesel and jet fuel. Fischer-Tropsch reaction generally include the following equation. Fischer-Tropsch synthesis on cobalt catalyst have been subject to thorough investigation since developed by Fischer and co-worker in the 1920s. Cobalt-based catalysts are of particular interest for industrial application due to high activity at low temperature, high selectivity toward long-chain hydrocarbon, and a long lifetime. A lower deactivation rate is usually found using cobalt catalyst under pure synthesis gas, but cobalt is more sensitive to impurity, and deactivation of catalyst in this research focus on sintering and poisoning. Literature review. Visconti study effect of sulfur poisoning in the range of 0 to 2000 ppm on the characteristic and catalytic performance in Fischer-Tropsch synthesis and use cobalt alumina unpromoted catalyst obtained by impregnation of alpha alumina with a cobalt nitrate solution. The cobalt loading was 15 weight by weight, and then catalyst sample load with 10, 100, 250, and 2000 ppm of sulfur. From fig 1 show positioning of the catalyst sample with sulfur lead to a significant decrease of the catalytic performance. At the lowest indicate sulfur level is 10 ppm that carbon monoxide conversion dropped to 18%. From this result that decrease of the carbon monoxide conversion that affect to decreasing in the productivity of reaction product and by change product selectivity. In the result, observe that carbon dioxide greatly increase upon poisoning the catalytic. So effect of sulfur poisoning strongly depend on the sulfur loading, possibly because different catalytic function are affected by sulfur. For nitrogen poisoning, little is known on the effect of nitrogen contaminate containing compound, and the available information is mainly found in patent. DVNS investigate the effect of ammonia cyanide and NOx by addition 110, 100, and 1200 ppmW. The result indicate that small amount of nitrogen contaminant have an immediate effect on the catalytic activity. Ammonia appear to poison cobalt metallic site to some extent. For sintering is main cause of deactivation and lead to a reduction of the active surface area. In 20 and 2, Bertot investigate the effect of water using rhenium promoted unsupported cobalt catalyst shown on fig 3. After water co-feeding with 4 bar of steam, run 30 and 32, and then when look at activity check 33, from the result show amount of adsorbed cobalt doesn't change, but both Kc star and KCO decrease. And when you see in activity check 38 after run 36, 37, 8 bar co-feeding, not only decrease both Kc star and KCO to 40 of the original value, but CO carbon monoxide inventory also decreased by approximately 35%, and activity check 39%. 39. Hydrogen treatment recover most 80% of the site activity. So the result loss of adsorbed carbon monoxide to cobalt surface loss due to sintering. Physiotop later by important synthesis in the future trend because of physiotop can use to reduce release of toxic gas into catalytic atmosphere, so it should have an improve of catalytic for more stability by first step before reaction. I think that should be sulfur treatment by desulfurization with hydrogen peroxide and eliminate of nitrogen poisoning effect by operate at my hydrogen. That can treatment for catalytic and then feed to reactor by using a combination of catalytic and RU promoter that it helps to giving a highly active sintering resistant catalyst for increased catalytic stability. A future, if it has improved overall performance of catalyst into a better way, it will help to reduce cost of operation. Thank you for your attention.
Thank you for Moramid. And the next is the Visansaya. Visansaya, please prepare your presentation. And the presentation will start in 2 minutes. Hello, Visansaya. Okay.
Can you hear me?
Yes, yes. Okay, Mr. Saya, you can start.
Okay. Hello everyone, my name is Cynthia Malemat. I'm going to start with litigation study of nickel-based spent catalyst from the reforming of methane. And the outline, of the topic is introduction, literature review, summary, and research direction. Okay, let's go to the next point. Our main is dry forming of methane. You must know this reaction very well because the forming of methane is important process to producing gas is suitable for methanol and future-top synthesis. Two main greenhouse gas is mixture of hydrogen and carbon monoxide, which can use in the production of energy and of hydrochemicals. If you see the side reaction, you must see carbon in the equation 2, 3, and 4. It's called coke. Coke formation is called of catalytic activation. Most of the research focus on improve of the physical-chemical property and optimize reaction to obtain catalytic conversion and stability. However, the capacity of regeneration of the catalyst is also important parameter. Three things that advantage for regeneration. First, regeneration process not destroy and not modify the structure of the catalyst. Second, environment friendly is not leaving spent cat to the environment. And the last one is safe cost. Safe cost is better than by-effect catalyst. Now we are moving to the new topic. Here is the development of regeneration study. First period of catalytic regeneration in the 2009 to 2011 are related to the combustion of coke with air. Also, the mechanism of carbon species oxidation by oxygen has been widely investigated. However, coke can be removed not only by oxygen but also by different gasifying agents such as steam and carbon dioxide. So study of regeneration use of gas, carbon dioxide are interested. Until 2017, development of the catalytic regeneration was started with using carbon dioxide. In 2018 until now, they are compared to different gasifying agents are air and carbon dioxide. Here is regeneration study by air. The catalyst is used bimetallic rhodium nickel support with boron nitride compared with rhodium nickel support with gamma alumina oxides. Catalysts were calcined in air at 300 degrees Celsius to remove carbon deposits. The results show that the activity of boron nitride support more than gamma alumina oxide support. So boron nitride is suitable for dry reforming of methane and the catalyst could remove the carbon formation. Next is the same regeneration study by air compared with hydrogen and nitrogen. The catalyst is used nickel cobalt supports with manganese oxide, selenium oxide. The catalyst was regenerated in the reactor for 1 hour under different gas regeneration. First stage regeneration by air could restore the catalyst performance to 84% conversion of methane. On the other hand, nitrogen and hydrogen did not improve the catalytic performance and the activity continued to decrease. The result proved that catalytic deactivation was unlikely to be caused by metal oxidation. It can say that the catalyst used in the present study was stable and easy to regenerate. Let's go to the next point. Here is the regeneration study by carbon dioxide. The catalyst is used nickel support with selenium oxide and the catalyst was treated in 1% carbon dioxide. In graph, you will see the in first 90 minutes, the rate on the three catalysts were similar and decreased with time on steam. At that point, the reaction was stopped and the catalysts were exposed to a stream of 1% 100 carbon dioxide for 90 minutes. After this step, the rate on nickel support with selenium oxide more than the other catalyst until the end of the experiment. Next point, I will show mechanism of carbon dioxide treatment. During regeneration in carbon dioxide, oxygen by dissolution leads to the formation of carbon monoxide by Waldrop reaction. When carbon dioxide meets coke, that leads to form carbon monoxide, and oxygen form carbon dioxide that form with coke. It can remove the coke formation on the spent catalyst. In 2018, start with regeneration study by air combined with carbon dioxide. The catalyst nickel support with hydroxide particide are used. It has high chemical and thermal stability. Moreover, it presents basic side that can reversibly absorb carbon dioxide and help coke removal. The reaction was run at 700 degrees Celsius under air and carbon dioxide. The results show that methane conversion and hydrogen reactivity with air regeneration are quite similar than carbon dioxide regeneration. The catalyst after regeneration stayed with both atmosphere away show high methane conversion than the spent catalyst in red column. And it concludes that this catalyst can easy to regenerate under different atmosphere. Next is the similar experiment but exchange support. The support is dendritic fibrous SBA15. The results show that the generation process can remove coke over the surface and pore of spent catalyst by gasifying agent without destroying the structure and composition of the catalyst. For the first circle, carbon dioxide conversion and methane conversion is at 90.61% and 90.44%. After 30 hours of the operating time, the results show that carbon dioxide and air regeneration cycle was totally different, and catalytic performance of air regeneration was better than carbon dioxide. It proved that carbon meets oxygen in air and form into carbon dioxide, which can remove coke into carbon monoxide. Show that air regeneration was more efficient than carbon dioxide regeneration for this catalyst. So to summarize, the main point of my talk is 3 points for the reforming of methane reaction. Nickel is the suitable catalyst for this reaction because its ion activity lasts reserve and so cheap. But this disadvantage of nickel catalyst is easy to deactivate. So there should be acceleration of support and improve of the efficiency of the catalyst. And the best choice for improved efficiency of the catalyst for removing coke is regeneration. In the last part, I will talk about the research direction for this topic. In my own summarize, I think that it should develop a catalyst that can regeneration either air or carbon dioxide by modifying active site or support. And for regeneration to gasifying agents, further tests are needed to optimize the regeneration step and remove the core shell carbon deposit. In addition to support, it's important to study with help to make less deactivation of the catalyst. And the last thing that development of the regeneration of catalyst by using carbon dioxide is important to further research. Thank you for listening.
Thank you, Ms. Asia. And the next is Suphanat. Suphanat, please prepare your presentation. And the presentation will start in 1 minute. Suphanat, can you hear me?
Yeah.
Oh, okay.
Yes. Can you hear me?
Yeah.
Referee, if you are done, please upload your score sheet to the course wheel. Thank you.
Good morning, everyone. My name is Suphanat Kantawanit. I would like to talk about the topic of regeneration of catalyst deactivated by coke deposition. For the outline is introduction, literature review, conclusion, and recommendation of the future work. Coke formation proceeds through chemical steps, but also involve the retention of coke species in the pore and on the external surface of catalyst. This is generally accept this coke formation follow three steps. Step 1, hydrogen transfer at acid site. Step 2, dehydrogenation of adsorbate hydrocarbon. And step 3, polycondensation. In principle, coke may affect catalyst activity two ways through active site coagulation and second is pore blockage. In this paper, we will discuss receive advance in coke removal using oxidation, gasification, and hydrogenation. First, regeneration using oxidation. In the work, we use non-thermal plasma to regenerate zeolite catalyst because it leads to the formation of highly active site species such as radical, excited atom, ion, and molecule. Under oxygen plasma, the most abundant species formed are the positive and the negative ion. This image show the plasma treatment lead to partial coke eliminate since the dish present a gray color compare the black color of the coke sample. And this figure is show show coke removal under plasma discharge. Percent coke removal in the center more than periphery because plasma start at the center and total percent coke removal equal 40%. And XRD pattern is show the phase and deactivated and regenerated HCSM5 zeolite in graph to theta equal 22 to 38 degree. The diffraction angle of HCSM5 zeolite were in accordance with HCSM5 zeolite in the range of 2 theta equal 22 to 25 degree compared with the XRD pattern of deactivated and regenerated HCSM5 that of phase 1. They seem basically similar to demonstrated that there were not significant change between deactivated and regenerated HCSM5 in crystal structure, but some difference can be found in shape and intensity of some diffraction peak in the range of 2 theta equal 35 to 38 degree and 2 theta equal 26.5 to 27 degree. The fresh HCSM5 had 2 diffraction peak, but the deactivated one only had 1 diffraction peak. Intensity of the single peak increased significant in the range of 2 theta equal 26.5 to 27 degree. Next, regeneration using gasification. In this paper, they compare the coke removal of the catalyst. The catalyst vanadium, potassium, alumina have highest coke removal equal 73.53 and lowest coke removal is alumina catalyst equal 58.62. And the last is regeneration has using hydrogenation. In the result, characterization of HCSM5 catalyst used in methanol conversion and treat in a stream of propane and isobutane at 693 Kelvin 12 hours. Percent coke content and percent loss of surface have decreased after treatment with use propane and isobutane by hydrogenation treatment process. Conclusion: regeneration methods such as oxidation, gasification, and hydrogenation had effective to remove coke in catalyst. Gasification method can transform the low-value coke into value-added syngas and reduce the carbon dioxide emission. At high temperature in regeneration method, catalysts were cracking because structure of catalyst is not stabilized. Recommendation of the future work: study regeneration kinetics that consider the catalyst active site. Second, synthesis of catalyst with excellent thermal and hydrothermal stability. Third, addition to the low the regeneration temperature. And the last, catalytic process with partial regeneration does not only increase carbon and utilization. Thank you for your attention.
Okay, thank you for Sapana. Next is Supavish. Supavish, prepare your presentation. And the presentation will start at 9:30. Okay, so you can start.
Good morning, everyone. I will present about regeneration of sulfur poison palladium-based catalyst. This is my overview of my talk. Due to high activity, palladium-based catalyst is widely used in industrial reaction, such as hydrogenation, dechlorination, steam reforming, and hydrocracking. Although full utilization of catalyst potential, palladium catalyst is very sensitive for poisoning and deactivation. The palladium species that we found commonly is palladium and palladium oxide. Poisoning is chemisorption between catalyst and molecule in the system. The poison molecule can be reactants, intermediates, products, or impurities. The poison molecule will block the active site and accumulate on the catalyst. The activity of catalyst will decrease slowly as the figure 4. And finally, there is no active site for reaction in the system. Prevention are the method to minimize the deactivation. The prevention way to avoid poison are the following. However, trace of poison molecule can deactivate catalyst, and sometimes poison molecules are products or intermediate. So, regeneration process is very necessary. Regeneration can recover the activity of catalyst. The key point of regeneration is to remove poison molecules from the active site. The method of regeneration for sulfur poison catalysts are thermal treatment, oxidizing with oxidizing agent, and chemical washing. The first is thermal treatment. Thermal treatment is the method that apply heat energy to the systems. The absorption is an exothermic process, so that increasing of temperature makes poison dissolve. For example, sulfur poison on palladium carbon catalyst. Catalyst is regenerated at 100 degrees Celsius for 8 hours. This figure shows that regenerate with hot air can recover more activity than hydrogen and argon. This because the air composed of oxygen, so oxidizing will also occur during the thermal treatment. Sometimes oxidizing is not good way for regeneration. For example, in this study, reducing atmosphere, that is low oxygen condition, to prevent the oxidation of sulfur, because alumina can absorb sulfate and cannot dissolve while these catalysts are regenerating. That made the conversion still decrease after regeneration in the absence sulfur dioxide condition. However, the thermal treatment is very popular and easy to do, but regeneration at high temperature, you have to concern about sintering of metal side. The second method is oxidizing with oxidizing agent. Each molecule of the sulfur compound has a different strength of the bond with the active side and can be sorted. These molecules form the least to the most as sulfate, sulfur dioxide, and sulfide, respectively. That can imply that the presence of oxygen can reduce the strength of the bond with active side, so that adding an oxidizing agent to oxidize the sulfur compound makes poison dissolve easier. For example, palladium catalyst in dechlorination of monochlorobenzene is deactivated by sulfide molecule, and we use potassium permanganate to regenerate this. to regenerate this catalyst. The last one is chemical washing. The chemical that commonly used in the oxidation of sulfur are very effective. On the other hand, they can destroy some type of support such as carbon support. So we consider to use the other chemical that's less harmful chemical. From this table, the chemical can recover surface. DMF, known as dimethylformamide, is the best, but surface area is small when compared with phase catalyst. So wash catalyst is still require more regeneration process. Conclusion: we can conclude that the point of regeneration of poison catalyst is to remove the poison molecule from the active site, and the method of regeneration are depending on metal site and type of support. In the future, we should improve the methods that can be used for all type of support, can regenerate catalyst at low temperature to avoid sintering, and be friendly to the environment. Thank you.
Thank you for Supavit. And next is Saharat. Saharat, please prepare your presentation. And the presentation will start at 9:41.
Can you hear me?
Yes, sir.
Yeah, okay.
Okay, Saharat, please start your presentation.
Hello everyone, my name is Saharat Bailak. Today I will present in topic platinum deactivation. I have about this topic. One, introduction. Why we use the platinum? Two, literature review. Information about the platinum as a catalyst. And three, research direction. The way to develop in the future. Introduction. Carbon monoxide is one most poisonous gas that released into the environment by incomplete combustion by mainly from transport sector. So many researchers research to how to reduce the carbon monoxide from environment, and that have many methods. Example, the water gas shift reaction. How to remove it? That I talk. Water gas shift reaction that can reduce the percentage of carbon monoxide in environment by using the catalytic converter to reduce it from the internal combustion engine, and use the platinum as a catalyst to increase the rate of chemical reaction. The platinum is that have the property to resist the corrosion and resist the high temperature. And when used, the catalyst is have a very good performance. And the platinum most used in the catalyst converter, lab equipment, and electrical contact or electrode. The water gas shift reaction that use the carbon monoxide and steam react that give a product is a carbon dioxide and hydrogen. The platinum deactivation that happen when the reaction had happened. A few of carbon that interact with the catalyst that reduce when the carbon cover the surface of catalyst that reduce the surface that increase the performance of the catalyst. And the second that thermal sintering when used reaction or operate in high temperature that made a crystalline growth of active site that made a high volume of active site but decrease the surface and that effect to decrease the performance of catalyst. Example of the paper or journal mechanism for water gas shift reaction on the monofunctional platinum and cause of catalyst deactivation. It's like the result is same the previous slide that experimental and theoretical result that suggest the carbon monoxide dissociate into pathway for the reaction and to a COH intermediate that mutation of carbon at step 8 and subsequent of agglomeration deactivate the catalyst. And another journal that is a support induction of platinum silicon oxide and platinum silicon carbide. Catalyst prepared by nano-platinum colloid deposition for carbon monoxide oxidation. Little that show the thermal sintering of the platinum that the temperature of operate that increase uh, the platinum growth in high volume but decrease the surface that effect to decrease the performance of catalyst. Research direction. And thus they need to develop technology that use clean energy. And we have to develop to bring the hydrogen to generate the electricity that used in car or industry to replace the vehicle or industry to use the petrol. That we use the platinum as a catalyst in SOEC or SOFG to produce the hydrogen. But today the platinum is a very high price to develop. Thank you.
Okay, thank you for Saharat. And the next is Sitthichai. Sitthichai, please prepare your presentation. And the presentation will start at 9:49.
โอเคครับ Can you see the slide?
Yes, I can see slide.
Okay, good morning, everyone. My name is Sitisha Ramrung. Today, I would like to present about role of tungsten oxide to improve the stability in terms of platinum leaching resistance on platinum alumina catalyst. The hydrogenolysis of glycerol is a catalytic chemical reaction that involves breaking a carbon-oxygen bond with simultaneous addition of a hydrogen atom. Firstly, on this route A, the secondary hydroxyl from glycerol is dehydrated into 3-HPA on acid side, which is then hydrogenated on metallic side into 1,3-propane-diol. The new more active and selective heterogeneous catalyst for producing 1,3-propane-diol from glycerol hydrogenolysis. This catalyst have a metallic function responsible for hydrogenation and acid function, which promote selective dehydration. The amount of platinum and tungsten leaching from the surface of catalyst in the reaction solution based on the catalyst used. For platinum on alumina catalyst, the loss of platinum active site through leaching play a significant role in the catalytic activity. And for platinum tungsten oxide on gamma alumina catalyst, addition of tungsten oxide can be related directly to the prevention of platinum leaching due to liquid phase and the effect of strong metal support interaction between platinum and the support caused by the tungsten components might play a role in a significant decrease in the platinum leaching. The EDX profile of platinum atom after the first reuse in figure J exhibits some platinum clusters suggesting the agglomeration of platinum active site. For figure K and L were similar, suggesting that doping with tungsten oxide help resist platinum leaching and also agglomeration. However, the resistance to agglomeration was not so clear via EDX profile. Thus, the role of tungsten oxide on agglomeration was investigated in XRD. On the reused catalyst, the platinum diffraction peak appeared at 2 theta of 39.9 degree in both systems, as shown in figure C1 and D1. The presence of such a peak indicated the growth of platinum atom into a large cluster. Therefore, both systems without tungsten promoter, the agglomeration of platinum is still present. Therefore, the platinum leaching plays a critical role in the determination of the catalytic activity and stability. The metal support interactions can be described by considering absorption atom energy. For absorption of platinum on tungsten oxide and gamma alumina surface is stronger than on gamma alumina. The strong interaction between platinum and tungsten oxide on gamma alumina surface can be described via the formation of 4 bonds. 2 bonds between platinum with oxygen of gamma alumina and the other 2 bonds between platinum with oxygen of tungsten oxide species. Therefore, a low platinum leaching found in the platinum tungsten oxide on gamma alumina is due to strong metal support interaction promoted through the gamma alumina surface and the tungsten species as well. For the change in surface electronic property analyzed by charge density difference and Butler charge change, figure A, the electron transfer from platinum to alumina support is verified by the electron gain in the support and electron loss from platinum as shown in table. Besides, the charge density difference reveals that the metal support bonding occur only between platinum and oxygen side. Figure B, on the tungsten oxide alumina interaction, the electron move in the opposite direction from alumina to tungsten oxide. Interestingly, the tungsten species are acting as an electron acceptor, withdraw electron from two nearby oxygen atom sites. The electron deficit of more oxygen side on the surface would lead to a higher tendency in the acceptance of the incoming electron-rich species. And figure C, the platinum tungsten on gamma alumina models determine the tungsten species to be even a stronger electron acceptor than when platinum is absent. The tungsten species now gain up to minus 2.91, while the electron loss in the support is lower than in case without platinum with the value of 1.77, and the platinum atom transfer electron to tungsten species, losing plus 1.14, which is much higher than when the is what in the platinum gamma alumina system. Therefore, the strong metal support promoter interaction found in the platinum tungsten alumina surface can be described in terms of electron transfer. That's the tungsten species acting as strong electron acceptor lead to an increase in contact point of platinum and the support. The strong metal support promoter interaction is the key in resistance toward lower platinum leaching during the hydrogenolysis process, resulting in a catalyst with high stability and should be the root cause of high activity in terms of glycerol conversion and high 1,3-propanediol selectivity. Conclusion, in the tungsten modified catalyst, the interaction between tungsten oxide and the platinum active site was strengthened to result in stronger platinum absorption to the support. This results in the strong metal support promoter interaction and stability of platinum agent leaching. Charge density difference and battle charge analysis suggests that more electron transfer from both the alumina support and platinum active site to tungsten oxide species than those between alumina and platinum in the platinum alumina system. In terms of resistant agents, platinum leaching, the strong metal support interaction be the main impact towards the activation. And the promoter that promotes strong metal support interaction or strong metal support promoter interaction would lead to highly stable catalyst for the hydrogenolysis of glycerol. Thank you.
Okay. Thank you for Sitishai. And next is Surimat. Surimat, please prepare your presentation. The presentation will start in 1 minute.
Can you see my slide?
Yes.
Okay.
Okay, Surimat, please start your presentation.
Okay, good morning, everybody. My name is Rima Sulian. Today, I would like to present about topic coke formation and deactivation during steam reforming with nickel catalyst support over alumina. And this presentation has 3 contents: introduction, literature review, and research direction. First, introduction. The butanol steam reforming takes place in the gas phase. It occurs in 2 steps shown on slide. Nickel catalysts are widely employed for steam reforming reaction due to its high activity in breaking CCOH or CH bonds. And alumina is overall the most employed support because of its high specific area. Next, for literature review. In figure 1, X-ray diffraction profile of support and catalyst in 3 different states: calcine, reduced, and after reaction. No nickel oxide peaks were detected in reduced catalytic profile, suggesting that reduction was efficient in converting all oxide species in metallic nickel. For all spent catalyst profile, nickel oxide peaks were not detected, indicating good stability of the metallic active phase during the reaction. Furthermore, a broad peak at 26 was observed in all spent catalysts related to coke deposition during the reaction. Nickel, magnesium, alumina catalysts exhibit the most entry peak, suggesting more significant coke formation. Figure 2 show SEM image of nickel alumina calcide sample and spent catalyst in order to evaluate coke morphology. It was verified mainly amorphous carbon for all spent catalysts. However, it was also observed that the encapsulation of catalyst particle occur mainly for nickel alumina and nickel calcium alumina, which correlate a more severe deactivation observed for this catalyst. For conclusion, nickel, magnesium oxide, alumina catalyst present the best performance for butanol steam reforming, and magnesium oxide addition resulting in lower coke formation by carbon convert formed mainly by CO disproportionation and a lower amount of encapsulation amorphous coke. Last, with research direction, study the effect of other catalysts or support species on butanol steam reforming, or study of the effect that can further cause a coke, such as an increase in temperature, system pressure, and more. Thank you for your attention.
Thank you for Sirimat. The next is Sutipon. Sutipon, please prepare your presentation. And the presentation will start in 4 minutes.
Can you see my slide?
Yes.
Start now.
Wait for 2 minutes. Sutipon, can you volume up your microphone?
Can you hear me?
Okay.
Okay.
Okay, Sudipon, you can start your presentation.
Okay. Hello everyone, my name is Sudipon Laksakit. Today I would like to present about the activation of platinum catalyst by Koch deposition. For the outline, first I will talk about the introduction, next literature review, and finally I will talk about the conclusion. Introduction, the problem in the reaction when catalyst is used for the long time. Most of the problem arise due to Koch deposition. Effect of catalyst deactivation is loss of the catalyst activity and loss of the product selectivity. Effect of coking is blockade of the active site, encapsulation and deactivation of catalyst, and plug the pore of the support. Next, literature review. In this paper, is focused on the deactivation of platinum support on zeolite KL during enhanced aromatization reaction. You can be seen from the figure A that the conversion of N-heptane was significantly decreased, meaning the activity of catalyst decreased, which was caused by the activation. But after regenerate, activity of the used gas was recovered substantially. Figure B shows that the selectivity of aromatic decreased with the time of steam, which decreased significantly, while the figure C that is the selectivity of olefin increased, and the figure D is the selectivity of hydrogenolysis product, which is relatively constant. From the figure, you can be seen that the platinum located on the external surface of zeolite crystal. At the figure A1, their particle size appear to have increased after 24 hours of the reaction at the figure D1. From the table 2, you can be seen that the Koch deposition significantly decreased the specific surface area and the micropore volume of the catalyst during aromatization reaction. It makes too rapid deactivation. The access to platinum particle within zeolite channel is blocked to the large contact exchange. This is dangerous for the catalyst because platinum support on zeolite is monofunctional catalyst and the platinum particle within zeolite are active sites. After regenerate, you can be seen the Koch cannot remove, it can be removed, but platinum particle cannot separate. For Koch content, it will increase with the time of steam. In this paper, I will focus on the deactivation of platinum support on zeolite KL by varying morphology and the channel length. This is a morphology of a zeolite where A is hockey puck, B is cylinder, C is the long cylinder, and D is cam. You can be seen that the figure B and C are cylinder and long cylinder, which is a long channel zeolite resulting is low platinum dispersion. This figure shows that the dispersion of platinum particle increased, the conversion of N-octane increased, which means that the activity depends on the dispersion of platinum particle. Table 5 shows that the activity is independent of dispersion of platinum particle only, but also with platinum location. In the case of cylinder zeolite and long cylinder zeolite, you can see that the more platinum location outside the zeolite channel, the lower activity. And in case of cam zeolite, the platinum location is quite high inside the zeolite channel, and no platinum particle outside the zeolite channel make the activity higher. This picture showing the conversion of N-octane. It will notice that the conversion value will decrease significantly at the initial. This refers to the activity of catalyst decrease. This is caused by the activation which can be ascribed to pore blocking by Koch. These two catalysts has higher platinum dispersion.
3 minutes.
From the table T, you can be seen that the base zeolite dispersed is calm zeolite. It is expected that the coke deposition may not depend on the platinum dispersion due to the relatively large coke dispersion, but it appears to be correlated with morphology of zeolite. And finally, conclusion. The activation of catalyst is aromatization reaction. The channel blockade caused by coke, which was mostly deposition inside the instar channel space near the channel opening, and large platinum particle on the external zeolite surface may lose in the formation of coke precursor, limit deposition of platinum particle within one dimension micropore may facilitate coke growth and dispersion. Therefore, to improve the stability of the platinum support on zeolite KL catalyst, there should be a high dispersion of platinum inside the micropore. It is also highly favorable to use nanosheet of zeolite KL instead of the larger zeolite KL crystal as a support. Thank you for your attention.
Thank you, Sutiporn. Next, Hatapon. Hatapon is prepare your slide and your presentation will start in 2 minutes.
You can see.
Yes.
The activation of star reforming nickel catalyst. First, introduction. Second, the activation mechanism. Last, design of anti-coke catalyst. Introduction. Which it is concerned about the remix amount of fossil fuel and the environmental cost of combustion fuel. To renewable energy source is biomass at low cost. Process biomass gasification. Chemical for implement and reforming reproduct with permission from reference. Biomass catalyst reforming easy catalyst deactivation. Reaction of reforming. Equation 1 with main products reforming, stream reforming. Equation 2 dies reforming of char. Equation 3 water gas ship equation. The activation mechanism of catalyst. Coke formation. One the major the case for the activation of catalyst during the char reforming reaction is coke. The coking is encapsulation of carbon material over active metal center case inhibition of active metal center to reactants. More possible carbon deposition during char forming is escorting reaction. You can see equation 4.6 as high reaction temperature, reaction 6 domain is formation of carbon. As low temperature, reaction flow dominate inside. Besides methane as other small hydrocarbons stacking, it's possible for the coke formation. Coke formation. Technical catalytic example show the coke mechanism in figure 3 with commercial nickel catalyst. It was steam reforming of biometallurgy production. Taiwan carbon deposition rates discrete cover of carbon active size block the enter of reactant the discrete activity. Actual carbon deposition fast is filtered from the active side and made from on support. Few factors can affect the carbon formation in the deforming reaction. First is particle size. The large active site between the large particle size for easy from carbon. Smaller graphene carbon ends up arresting the vital particle. Second is temperature and spectrum. With a higher reduction temperature and low reaction temperature, the cooking rate was the highest. The mass of carbon amorphous excess of graphene, so the carbon was easy removed by steam and active maintenance at high level. Third is type metal support interaction. To the kind of carbon nanotube from mechanism applied depending on the type of aluminum oxide support. Use nickel catalytic beds from steam reforming of sodium base. So mechanism was prefer a nickel gamma aluminum oxide interaction between metal and support very strong. So carbon nanotube convert nickel active size were from nickel alpha aluminum oxide typical mechanism was dominated relative weaker metal support interaction. So the metal dispersion was higher than nickel gamma aluminum oxide support, leading to the higher yield of hydrogen. The activation by sulfur poison. Sulfur is easy convert to hydrogen sulfide. You can see equation 7. Sulfur poison effect in general taking nickel as sample metal nickel sulfur.
3 minutes left.
Design of anti-coating catalyst during tar reforming reaction. Diffusion from tar mixing of spring fossil hydrocarbon is not removed its time leading to a loss of active surface area. The activation of catalyst and for catalyst performance. First, absorption of water carbon to the from surface hydroxyl or oxy group carbon carbonates. Surface active species such as hydroxyl and oxygen containing group with benefit remove of carbon. Redox property of transition element, the rare element and all apparent earth element to the provide oxygen when vacancy. Active oxygen surface oxygen species. Transition element rise iron cobalt Mn and copper could promote the coke removal. Thank you.
Okay, thank you, Hatapon. Next, Episada is prepare your slide and your presentation will start in 1 minute. Okay, Pisada, you can start your presentation.
Good morning, everyone. My name is Afisada Rongsalat. Today I'm going to be talking about, co-resistance of nickel-based catalyst in butanol steam reforming reaction. And my outline is going to be introduction, literature review, and conclusion and research, including research direction. As you have already heard, many of our classmates talk about the concern of global climate change due to the use of fossil fuels. The alternative energy source has been proposed in order to reduce carbon emission and greenhouse gases. Researchers grow the interest in producing hydrogen because it doesn't produce carbon when you burn it, and it can use as energy source for many applications such as fuel cells. We're familiar with the methane reforming, whether it's dry methane reforming or steam methane reforming to produce hydrogen, but there has been researches using butanol as feedstock, which can provide more hydrogen than using methane as feedstock. And there has been a study about butanol reforming using nickel alumina catalyst with the promote of alkali earth oxide. They study the effect of alkali promoter, which are magnesium oxide and calcium oxide, on co-resistant in butanol steam reforming. The reason in using the temperature of 500 Celsius is because according to Hong, who study about the effect of temperature on butanol steam reforming at the range of 400 to 800 Celsius, they have found that with the increase of the temperature, the hydrogen yield will increase. But if the temperature go beyond 800 Celsius, the hydrogen will decrease due to the acceleration of the reverse water gas shift reaction. The authors of this research calculate gift-free energy minimization and enthalpy variation for butanol steam reforming. The data calculated at 500 degrees Celsius were used for all reactions present in this work. Nickel is used as active metal because it's abundant in nature, high activity and low cost. And for the support, they use alumina because high specific surface area and high dispersion of active metal. And the promoters, there's been report that magnesium oxide and calcium oxide in steam methane reforming will enhance catalyst stability and activity, and also promote rapid decomposition dissociation of methane and carbon dioxide. And there has been report that molybdenum, lanthanum, calcium, and magnesium oxide on nickel gamma alumina will improve catalyst stability due to the same reason of promote rapid decomposition and dissociation of methane and carbon dioxide, and also prevent coke formation. And Medrano and the team compare the addition of calcium oxide and magnesium oxide on nickel alumina for butanol steam reforming. There has been found that the metal has the low dispersion and lower catalytic activity for the promoted catalyst. So the objective of this study is to improve the catalyst preparation method using, first of all, cold precipitation for the support and wet impregnation for nickel phase incorporation. An experimental method can be categorized to three steps. And I will not go on detail of how they prepare the catalyst, but the catalyst preparation, as I mentioned before, they use the cold precipitation methods for the support preparation and metal disposition by wet impregnation. And 3 catalysts has been prepared as nickel alumina, nickel calcium alumina, and nickel magnesium alumina. And for the catalyst test, to see the performance in terms of the activity and stability of the catalyst, they took place in fixed bed reactor. And the last one is the catalyst characterization, with several methods have been used, such as surface analyzer, XRD, temperature program, SEM, and TGA. For the result and discussion, the first one is surface and textural properties. Basically, with the presence of the promoter, the surface area decreased due to the incorporation, the promoters and the support, and the alumina content also decreased. Surface area decreased with the addition of nickel oxide, except for nickel calcium alumina due to the pore blockage during wet impregnation. and the calcination temperature of 500 Celsius surface area will decrease and the pore size will increase when used 10 weight% calcium oxide due to the sintering during the calcination and pore blockage. For the XRD pattern, can categorize to 4 steps, which are catalysts before calcination, calcite, reduce, and spent catalyst. The result has shown that there's no peak of magnesium oxide promoters indicate to good dispersion and no crystalline phase. Calcite sample peaks indicate that nickel nitrate has converted into nickel oxide. For the reduced sample, all catalysts can be converted into all oxide species. And for the spent sample, nickel oxide is not detected, indicates a good stability of active phase. For the reduction profile for the nickel, calcium, alumina give the highest reduction degree because of the more reducible species. And for the desorption of ammonia, the magnesium promoter give the highest basic promoters, and the magnesium oxide addition provide a decrease of ammonia consumption from 3.1 to 1.1 due to the higher dispersion. For the carbon dioxide desorption, the nickel alumina has only weak basic size, and the nickel calcium alumina have the weak and moderate basic size. And most intense peak is at 790 degrees Celsius, indicates to carbon dioxide absorption and bulk calcium oxide species. And for the catalyst test, the nickel magnesium alumina conversion is 100% during the reaction without any deactivation. But for the other two, the activity decreased due to the coke formation.
1 minute.
And I'll give you the future prospect because the time is run out. The suggested method is using the nickel-based catalyst with the higher oxygen storage. There are many ways to use it, but the way to use it that is very interesting is use the support of titanium oxide, because with the presence of titanium oxide, it will reduce the coke formation, and it will also eliminate the deposition impact lattice oxygen on eliminate coke formation. And for my conclusion, butanol steam reforming increased hydrogen yield compared to the steam methane reforming because but the problem with the reaction is the coke disposition. By using magnesium oxygen promoter, catalyst has the highest performance, and it also help with coke resistance. To do the suggest method to reduce coke formation further, nickel-based catalyst try using the support of titanium oxide could help with the coke resistance, and humid reaction environment could help the occupy of oxygen vacancy and the absorb on the surface of titanium oxide facilitate to remove of carbon disposition, and absorb water can lower the activation energy and facilitate the occurrence of energy. And the last one, research direction. The first one is try study the feasibility of using titanium oxide as a support compared with alumina. The second one is study the use of other promoters. And the third one is optimize the condition using butanol steam reforming using titanium oxide. Thank you for your attention.
Okay, thank you, Apisada. And next, Atitaya, you can start presentation.
Hello.
Yes.
Can you see my slide?
Yes.
I'm start now.
Yes. Start.
Good morning, everybody. My name is Aditya from Thongkeo. Today, I'm going to present you about enhancement of carbon dioxide methanation over nickel-based catalyst. Table of content, introduction, literature review, and future direction. Let's see first section, introduction. The increase of atmospheric carbon dioxide emission is creating some social and environmental issues. Carbon dioxide hydrogenation has been regarded as one of the promising strategies to reduce carbon dioxide as carbon resource and produce high value add chemicals such as methane. The carbon dioxide methanation, namely hydrogenation of carbon dioxide to methane, has significant in coal to gas for clean utilization of coal, power to gas for renewable energy storage, and carbon dioxide removal for spacecraft. This figure shows the reaction of carbon dioxide methanation in exothermic reaction. And why use nickel-based catalyst? Is what highly selective toward the formation of methane. Price is much lower compared to those of noble metal catalyst. Its use is more favorable in industrial application. What about problem? The stability of nickel-based catalyst is often compromised by the activation due to sintering and carbon deposition. And the sintering enlarge metal site and decrease active site, while carbon deposit encapsulated catalytic surface and hinder contact of the reactant. And how to improve the catalytic performance and reduce the deactivation problem. Section 2, literature review. First paper study about catalytic activity and stability of the nickel-based catalyst prepared by different methods. The figure shows the stability test of catalyst for carbon dioxide methanation. You can see that lanthanum-modified catalyst show better catalytic performance than nickel on support, and nickel lanthanum oxide on support prepared using a citrate complex method found to have a high catalytic performance toward carbon dioxide methanation. Due to the specific perovskite structure of lanthanum nickel oxide, the interaction between lanthanum and nickel was intensified, which contribute to the high dispersion of nickel nanoparticles as well as good anti-sintering and anti-carbon deposition property. Second paper study about catalytic activity and stability of cobalt-doped nickel-based order mesoporous catalyst for carbon dioxide methanation. The figure shows catalytic property of catalyst. The order mesoporous 10N3COMa, that addition of 10% weight of nickel oxide and 3% weight of cobalt oxide catalyst show high activity and high stability and superior anti-sintering property during 500 degrees Celsius 60-hour lifetime. This work show that the other mesoporous nickel cobalt on alumina support catalyst is a promising candidate for carbon dioxide methanation, which can simultaneously prevent sintering of metal particles while maintain high catalytic activity at temperature. Third paper study about catalytic activity and stability of nickel-based catalyst over different support and different nickel loading.
The catalytic activity strongly depends on nature of nickel oxide interaction. The figure shows nickel on cerium oxide catalyst deactivate quickly due to coke accumulation. And this figure shows the moderate nickel support interaction explain the superior performance of the lithium support catalyst, for which higher the nickel content and higher the activity. Activity data for nickel on lithium catalyst were closely related to the degree of nickel dispersion as well as to the medium strength basicity. Good anti-coking and anti-sintering ability were observed after 200 hours of lifetime. And future direction. Modify nickel-based catalyst with other material or other synthesis method that can reduce sintering and coking. Use various support on nickel-based catalyst that provides strong metal support interaction.
1
Use
minute.
various dose of metal on nickel-based other mesoporous catalysts such as cobalt, ruthenium, and very metal content. Use calcium nickel-based catalyst that provide excellent unique feature of sintering-free and low carbon deposition in high temperature. Thank you for your attention.
Thank you, Atitya. And next is Eburut. Eburut, prepare your slide and your presentation will start now. Okay, you can start your presentation.
Hi everyone, my name is Ekburut. Today I would like to present on the topic is the stability and regeneration process using nickel-based catalyst in dry reforming. This is our outline for today. First, let's start with the introduction. As everyone knows nowadays, the greenhouse gas in the atmosphere has been reached. So it is necessary to mitigate the carbon dioxide emission by development, reuse, or revolatilization technology. So the production of synthesis gas from greenhouse add carbon dioxide reforming or dry reforming to produce hydrogen and carbon monoxide was proposed. And in this process, there are many metals for catalytic process, such as ruthenium, cobalt, nickel, or platinum. But in this presentation, I will focus on nickel catalyst. For the literature review, for this paper to develop an effective nickel-based catalyst support on gamma alumina with magnesium oxide, calcium oxide, and barium oxide. In the figure 1 show the methane conversion and carbon dioxide conversion. You will see that the magnesium, after adding the catalyst, they will give the highest conversion with the methane conversion and carbon dioxide conversion. And then in the figure 2 show the methane conversion with time. It is show that magnesium also gives the highest methane conversion along with time during the 300 minutes. And this figure show about the TPO profile. In number 1 is that pure nickel. It show peak that appear at 500 and 700 degrees Celsius, which is referred to amorphous and filamentous carbon. But after adding the magnesium, calcium, and barium, it can be reduced in this to peak because it will be enhance the basicity of the catalyst, which can be increase the carbon dioxide absorption. And for this paper, they propose a series of aerogel nickel alumina catalyst were prepared by using a gel method combined with a supercritical drying. In the table 1, you can see that the aerogel catalyst give the smaller nickel particle size when compared with the impregnate catalyst. And the smaller nickel particle size would be beneficial for suppression of carbon deposition. And in the table 2, aerogel also give the less of deposits carbon slower than the impegnous catalyst, which means indicate that is better for coke depositions or resistant to sintering. And figure 7 show the FSEM image. In number 4 is a impegnous catalyst. You will see that it have a filamentous carbon cover or the active side of catalyst, which mean characteristics of graphitic carbon, which mean the main cause for sintering of catalyst. And in the Pearson's work, nickel yttrium aerogel catalyst was to as a novel catalyst to improve the coke resistance. You can see in the table 3, after adding the yttrium, it can be reduced the coke deposition in each temperature, and the lowest coke formation occur at 800 degrees Celsius. And research directions, all of these equations show how the carbon formation during the reaction, and all of equations show how to remove the carbon on the surface of catalyst by gasification. And
3
you can
minutes
see
remaining.
of process, which is a carbon dioxide as one of the reactant that we feed. So self-regenerates catalyst by using carbon dioxide as an oxidant that we should focus on in the future. Next is the plasma assist in reforming reforming methane. It's an innovative method for oxidation, but it have a limit in terms of yield for this size product is low. So we have to find the appropriate catalyst to use in this plasma reactor. And the last one is a dual function material as an additive catalyst for use in carbon capture storage. They are contain two parts. One is a alkali earth such as sodium, potassium, and calcium that can be absorbed the carbon dioxide, and one part is a noble metal which can be promote the reaction. And this is how conceptual of the dual function material. And the strategy to improve the nickel-based catalyst in the future. First is study the longer hours experiment by using the presence catalyst, which is nickel yttrium, which can be self-regenerated by using the carbon dioxide as a resistance for coke removal. Second is study the probability of nickel yttrium catalyst in plasma reactor, and finally is study using nickel yttrium catalyst in carbon dioxide storage regeneration technology. And this is my presentation. Thank you for your attention.
Thank you, Ebulut. And next is Atashai. Atashai is prepare your slide and your will start in 1 minute.
Can you hear me?
Yes. Okay, you can start your presentation.
Okay. Good morning, everyone. Today, I would like to present in topic of the sintering of T-way catalytic converter. The first of all, I would like to introduce you about the T-way catalytic converter before. The T-way catalytic converter is the catalyst that can change the toxic gas from gasoline engine, that's either NOx and carbon monoxide and some hydrocarbon into the harmless gas, that is nitrogen, carbon dioxide, and also water. This equation, chemical equation right here is the reduction of nitrogen oxide and carbon monoxide oxidation, hydrocarbon oxidation. The main catalyst that's used in the T-way catalytic converter or TWC is the platinum, palladium, and rhodium. Two key contributors to high catalytic activity are the surface area and depression of the pressure metal nanoparticle, right? Over time in operation, the active precious metal nanoparticle will subject to catalytic goal due to sintering that is resulting in reduced activity, even to the point of total deactivation. This figure, I would like to show you the two hypotheses for sintering that come from catalytic migration and also atomic migration. Sintering of active precious metal nanoparticle is closely related to reaction temperature and the size and composition of nanoparticles. When quasi-liquid layer form on the crystal surface, migration of the atom and crystalline will occur at the Higgs and Raman temperature of bulk phase that are often used to describe the temperature at which atomic migration and catalytic migration can occur. The ratio of the melting point of unique particle and the bulk phase, T0 right here, can be given by equation where gamma is the surface free energy, rho is the density of the solid and liquid, T melting is the melting point of unique particles, L is the heat of fusion, and T0 is bulk phase temperature. In this table, I would like to show you about the T0, T gamma, and T Higgs of the platinum, palladium, and rhodium, which are their components. The metallic platinum, palladium, and rhodium have higher Higgs and Raman temperature than corresponding compounds. Demonstrating that higher valency metal may have poor thermal stability. From previous slide, the experimental observation show that temperature is dominant factor for sintering, right? The sintering behavior of the active precious metal can also be affected by any other condition that lead to change in the surface energy of the particles, such as reaction, atmosphere, shape and composition of the metal nanoparticles, metal dispersion, the loading of the metal on support, and the last one is the interaction between the support and metal. Okay. Higher durability requires a lower sintering rate to maintain enough metal surface for a long-term use, and this is often accomplished by stabilizing the active metal nanoparticles. This slide, I would like to show you three typical strategies for precious metal sintering suppression in TWC. First one is the support anchoring for metal nanoparticles. Second is alloying of active metals. And the last one is the inhibition of atomic catalytic migration with support encapsulation technology. In TWC, precious metal sintering is difficult to suppress by support occurring due to the flocculation of extra gas composition and the temperature under operating condition. In addition, support occurring effect only occur at given temperature windows. For study to alloying by introduction of the second metal, which are a higher melting point, is a simple and more controllable way to control metal sintering and improve thermal durability. Hence, additional composition and content optimization of bimetallic catalyst is better cell stabilization effect.
3 minutes left.
Of great important. For the third strategy, support encapsulation technology can form additional metal support interface, but both the stability of shell in cold shell nanostructure catalyst and the cost of atomic layer disposition technologies still require further technical breakthrough. Okay. For future direction, in my opinion, The use of alloying effect to stabilize precious metal nanoparticle is very helpful for improvement of thermal durability, further optimizing the composition and content of the alloy and reducing of undesirable metal support interaction still pose key challenge in T-way catalytic converter application and manufacture. Thank you for your attention.
Okay, thank you, Antashai. And next is Chantip. You is prepare your slide and your presentation will start in 1 minute.
Okay, good morning, everyone. Today I'm going to talk about understanding the deactivation behavior of platinum tungsten oxides on aluminum oxide catalyst in the Gislaw hydrogenolysis reaction. Gislaw is one of the byproducts of the productions of the biodiesels, and it is being considered as a renewable feedstock for the productions of the high chemical value, such as 1,T-propanediol. Because 1,T-propanediol can be used as a monomer for the productions of the polydimethylene terephthalate. And this slide shows the market trends of the 1,T-propanediol is higher in the each year. And this slide shows the also the combinations of the platinum and tungsten oxides on aluminum oxides can be improved activity and selectivity, but it can be activated by leaching and accumulations. It's very difficult to avoid. So today I will present the mechanisms of the activation of this catalyst based on in this paper. And this slide shows the activities as a function of time on steam, and we can see that the conversion is declines the lipid and why is that? I will show you in the next slide. And this slide shows the textural property of phase and span catalyst, and the result shown in the figure 2 and table 1. And from the result, we can see that surface area, the pore volume, the pore size distribution remain unchanged at a long time on steam. And so from the results, we can confirm that the activations were not caused by the textural change of the support corresponding to get hydrothermal stability. And to check the leachings of the active component at the long-term reactions, in the results, we can see that the tungsten content dropped from the 9.1 to 7.8%. So to check the reachings of tungsten components were responsible for the deactivations of this catalyst, when we analyze tungsten concentration in the liquids at various times, the result shown in the figure in the table 2, and we can see that when the tungsten decrease, it did not affect to the deactivation rate. So from the results, we can conclude that the leaching of tungsten in this reaction was not dominant reasons for the deactivations of this catalyst. And this slide shows the results of the X-ray diffractions to determine the crystal structure of the phase and span catalyst. And from the results, we can see that for the span catalyst has a new peak at 39.8, indicated the refractions of the platinum 111 and can be described as the accumulations of platinum nanoparticle during the long-term reaction. And to check the accumulations of the catalyst, we can confirm by using HAADF-STEM's analysis, and from the result as shown in the figure 4. And we can see that the main size of the platinum particle size distributions of this catalyst before the stability test show at 1.9 nanometer, and after the reaction, the platinum particle go up to the 3.1 nanometer. And In addition, they use carbon monoxide chemisorption to measure the change of the platinum dispersions. And we can see that the phase catalyst has a platinum dispersion around 29.1. And after the reaction, the platinum dispersion dropped down to the 10.1. And from the results, we can conclude that the decreasing of the platinum size affect to the decreasing of the activity. In addition to the accumulations of platinum particle, coking is another possible reason for the deactivation. And we can confirm by using TJ and TPO analysis. And this slide shows the results of the TG. And from the profile, we can see that we have a two-state weight loss. In the first state, indicated the evaporations of the physical water as of on the surface. And the second state indicated the combustion of the coke on the surface. And this slide shows the TPO profiles of spent catalyst, and the result we found that the water and carbon dioxide were formed at 320 degrees Celsius, and can be confirmed that the coke contains both the bonds of the carbon and hydrogen. And after when we remove coke by 3% oxygen in helium, we found that the activity was not recovered. So from the results suggest that coking is not the major reason for the catalyst deactivation. And in addition, this paper you investigate the roots of the tungsten on the stability of the platinum active sites on gamma alumina by using the experimental data combined with the FT analysis. And from the results, we can see that when we dope the tungsten oxide, it affects to the harder of the leachings of the platinum active sites. And why is that? From the DFT analysis, we can see that when we dope tungsten oxides, it affects to the provide the higher absorption energy, indicated a strong interaction between between platinums and support when we compare with the catalyst without tungsten. And
2 minutes left.
And these reasons we can conclude that the effects of tungsten leaching may be affected to the accumulations of the platinum particle. And for the conclusion, the accumulations of the platinum nanoparticle took place with the time on steam, and it caused significant decrease of the platinum dispersions and leading to the deactivation of the catalyst. And for the suggestions to prevent the deactivation should be develop the extended the interactions between platinum and tungsten oxides, and consequently to limit the growth of the platinum particles. And today, thank you for your attention.
Okay, thank you, Shantip. And next, Lapipong is prepare your slide, and your presentation will start in 2 minutes.
You can see my slide.
Yes. Okay, Mr. Lapipong, please start your presentation.
Okay. Good morning, teacher and friend. My name is Lapipong Nawachala. Today, I am going to present the topic of the activation of cobalt catalyst during vegetable synthesis. For the outline my presentation, I had divided into 3 parts. That's composed of introduction, literature review, and conclusion and research direction. Let's begin in the first part with the introduction. The vegetable process was discovered by original German inventor during World War II that provided the liquid hydrocarbon fuel for the German. Vegetable synthesis is a surface polymerization reaction between hydrogen and carbon monoxide take place on the surface of the catalyst. And in the figure 2, represent a process diagram with starting at a gasification of natural gas, coal, or biomass to generate syngas, and then sent to vegetable reactor for polymerized hydrocarbon. And cobalt-based catalysts are mostly used in vegetable process due to highly active and long lifetime for this process. Let's move to the next part is the literature review. For the cobalt deactivation during vegetable synthesis, have two apparent lithium composed of lithium A and lithium B in the figure T. Lithium A is the first initial deactivation with link with a reversible deactivation, and lithium B that had a long-term deactivation associated with an irreversible deactivation. And the mechanism of cobalt deactivation was founded into 5 types composed of poisoning, coking, sintering, addition, and leaching of active phase. But I will focus only the first type. This slide presents a poisoning in vegetable synthesis. Poisoning is a chemical type of catalytic deactivation with strong chemical absorption of sulfur on a catalytic site. Sulfur is usually present in the feedstock, such as biomass and coal. And here, the limit sulfur content in the feed was proposed already by Fisher at 1 to 2 mg per cubic meter, but currently should be kept below 0.02 mg per cubic meter. In figure 4, show the effect of poisoning over cobalt alumina catalyst. When a researcher adding sulfur in a range 0 to 2000 ppm, the result show up morphological not change in the catalytic characteristic, but carbon monoxide conversion is decreasing at higher sulfur content, and the product selectivity is shift toward lighter hydrocarbon at a high sulfur loading. And second type is sintering. Sintering is a thermal and chemical deactivation, and commonly take place at high reaction temperature more than 500 degrees Celsius. And Fischer tube synthesis can produce a water along with desired hydrocarbon product. And sintering of cobalt crystalline may be accelerated in the present water. The water effect on selectivity product. It was indicated that the higher carbon atom selectivity increase. In the figure 6 represent a crystalline migration of cobalt. As you can see that a cobalt metal located nearby 8 outer and touch to heating between them, and the correlate at the end. In this slide show coking during vegetable process. A possible carbon formation that cause to deactivation. Since carbon may interact with the metal and form inactive species bulk carbide, or for species that may act as a reaction inhibitor, such as a graphitic and polymeric carbon. Metal carbide was detected by XRD technique as shown in the figure 8, and a long chain hydrocarbon product such as wax in the vegetable synthesis may accumulate and block microporous channel, and that affect to conversion decrease rapidly. And the one method for eliminate metal carbide is hydrogen treatment at low temperature. And another method is some noble metal such as ruthenium may be decrease carbon formation. For the last part is the conclusion and research direction. And conclusion of cobalt deactivation during vegetable synthesis. Cobalt catalyst in vegetable synthesis can be deactivated various mechanisms.
1 minute left.
Sulfur and alkali metal are affecting catalyst performance, and water may accelerate sintering. And high molecular weight carbon species will affect the activity due to diffusion inhibitor and poor parking. For the research direction, I think a research direction in the future is finding new technology to prevent or eliminate catalytic deactivation. And I divided into two ways. The first way is modify catalyst. For example, change some material, active phase, support, and promoter, and modify preparation method, modify commercial catalyst shape, and apply computational technique for the investigation of catalytic deactivation. Second is develop process. For example, modify process pretreatment feed to reduce poison in feedstock, and design of reactor geometry, reactor type, thermal operation, and catalytic packing. And last one is a develop regeneration unit. Thank you for your attention.
Thank you, Mr. Rapipong. Next is Wallace. You prepare, you present, and you will start in 2 minutes.
Good morning, everyone. My name is Valathong Sichat. Today, I will present about the topic of sulfur poisoning in nickel catalyst. The outline in my presentation consists of 3 parts: introduction, literature review, and conclusion. The first part is introduction. Nickel catalyst is a good catalyst for many processes, for example, SMG production for biomass, methanation, and methane reforming. For the above process is dissolved in sulfur poisoning in nickel catalyst and make the loss of active site, causing the deactivation of nickel catalyst. The second part is literature review. For this first paper focus on nickel aluminum oxide based catalyst sample, which had originally been deactivated by sulfur poisoning. The sample has been collected from a methanation reactor. Nickel catalysts were analyzed to elucidate the chemical nature of the sulfur poisoning species. The result from analytical tool was capable of revealing unmistakably that the catalyst had been poisoned by thiophene and not by hydrogen sulfide. This conclusion was researched by comparing the spectrum of the deactivated catalyst with that of model hydrogen sulfide and thiophene poisoned catalyst. For this second paper, study about sulfur deactivation mechanism during an industrial methanation process, but also after catalyst degeneration. Summarize the information presented above. A possible mechanism of surface process occurring during the methanation shown in this figure, including concepts base catalyst, reduced catalyst, initial state of working catalyst with carbon whisker, as well as sulfur deactivation and catalyst after regeneration, with remaining carbon and sulfur poison. However, part of stable sulfur carbon compounds stay at the support and lead to a repoisoning of the recovered nickel surface with the regenerated catalyst. For this third paper, study about effect of water on sulfur poisoning in nickel oxide catalyst. The adsorbed sulfur in the sample evolved in the form of sulfur oxide in the TPD. From the mass to charge ratio equal to 64 signal, it is seen that there is significant more sulfur dissolving from the catalyst surface when water is co-adsorbed. Moreover, it is also seen from the sulfur dioxide signal that there is some sulfur species dissolving from the catalyst at lower temperature when water is co-adsorbed. This result indicates that there is greater surface interaction of hydrogen sulfide in the presence of water and also a lower temperature surface realignment taking place over the nickel oxide catalyst. For this fourth paper study about hydrogen sulfide and sulfur dioxide poisoning in nickel catalyst during methane reforming. In the study of sulfur poisoning by hydrogen sulfide, the activity of all the measureless hydrogen sulfide concentration show a strong decrease at the beginning of sulfur poisoning. With the passing of the time, the deactivation approach to zero hydrogen sulfide is preferentially adsorbed at the most active nickel site of the catalyst, resulting in a strong decrease of the catalyst activity, especially at the beginning, for hydrogen sulfide poisoning during steam reforming of methane. In the study of sulfur poisoning by sulfur dioxide, the characteristic of catalyst poisoning remained the same no matter whether sulfur was fed to the inlet of the reactor as sulfur dioxide or hydrogen sulfide. In summary, the results show that sulfur poisoning by hydrogen sulfide was more pronounced than sulfur poisoning by sulfur dioxide. In the study of influence of oxygen-methane ratio of hydrogen sulfide poisoning, oxygen is preferentially adsorbed on the nickel surface of the catalyst, which helps to surface the formation of stable nickel sulfide and acceleration of the chemical reaction in thus expected. The reaction of catalyst poisoning due to the addition use of oxygen was also observed in the catalyst in the physical appearance of the catalyst after 7 hours of measurement. As oxygen methane ratio of 0% was adjusted and shown in figure B. The catalyst was fully covered with coke deposit and sulfur compound. Moreover, part of the catalyst were broken off, and the surface of the catalyst has a pronounced appearance. By contrast, the catalyst shown in figure A with an oxygen methane ratio of 60%. Only small change in the appearance of the catalyst compared to the initial state were observed, and these were mostly on the contact point of the catalyst. Black area on the contact point indicates slight formation of carbon or sulfur compound. For the conclusion, in the study effect of water on sulfur poisoning found that oxidation sites are less susceptible to sulfur poisoning, and that the presence of water in the feed increased deactivation due to sulfur. Hydrogen sulfide and sulfur dioxide is preferentially adsorbed at the most active nickel site of the catalyst, resulting in a strong decrease of the catalyst activity, especially at the beginning. For hydrogen sulfide and sulfur dioxide poisoning during steam reforming of methane, the experiment also show a rapid deactivation of the catalyst at the beginning and a reduction of the deactivation rate with the passing of time. In summary, the results show that sulfur poisoning by hydrogen sulfide was more pronounced than sulfur poisoning by sulfur dioxide. The addition of oxygen greatly influenced catalyst poison in terms of the finally least activity. Oxygen is preferentially adsorbed on the nickel surface of the catalyst, which help to surface the formation of stable nickel sulfide. Thank you for your attention.
Thank you, Valat. And next is Supakit. You are prepare your presentation and you will start in 2 minutes.
Did you hear me? Hello.
Yes.
Okay. Good morning, everyone. My name is Sujit Gavadit. Today, I would like to talk about carbon deposition in ethanol steam reforming over cobalt on silicium oxide catalyst. My presentation consists of 4 main sections from introduction to conclusion. First, introduction. The environmental impact for massive using of fossil fuel on the emission of greenhouse gas result in the rising of world temperature. The environmental goal of decreasing atmospheric carbon dioxide by switching in part to renewable resource, combined with the low cost of sugarcane. Ethanol is an attractive option for the hydrogen production since it is less toxic and can be produced renewably from biomass without addition of carbon dioxide to the atmosphere. Steam reforming is the main route for produce hydrogen from ethanol, as it gives the highest of hydrogen yield, and it is advantage of cobalt metal and silicium oxide support. For catalyst deactivation, the mainly cause of catalyst deactivation on cobalt or silicium oxide catalyst in ethanol steam reforming is from carbon or coke deposit. Cause of coking is from byproduct of ethanol steam reforming such as acetaldehyde, ethylene, acetone, carbon monoxide, and methane. The figure 1 shows reaction pathway for catalytic of ethanol steam reforming. Acetaldehyde is produced from ethanol dehydrogenation, and acetaldehyde can lead to coking or produce methane, carbon monoxide, and acetone, and continue to coking. Ethylene is produced from ethanol dehydration, and ethylene leads to coking. For acetone is produced from aldol condensation. There is no acetone in figure 1, but acetone can lead to catalyst deactivation as well. For carbon monoxide and methane, disproportionation reaction of carbon monoxide and cracking of methane is the major reaction responsible for formation of carbon deposit at low reaction temperature. Favor formation of carbon to carbon monoxide disproportionation reaction and reverse of carbon gasification with water, whereas at high reaction temperature, the formation of carbon through methane decomposition. For factor influencing carbon deposition, there are many factors that affect carbon deposition on cobalt on silicium oxide catalyst for ethanol steam reforming, such as reaction temperature, water ethanol molar ratio, catalyst preparation method, cobalt content, and I think cobalt dispersion on catalyst and nanoparticle in catalysis will be studied to improve performance and stability of catalyst in the future. In my presentation, I will talk about effect of reaction temperature and water ethanol molar ratio to carbon deposition over cobalt on silicium oxide catalyst for ethanol steam reforming. For effect of reaction temperature to carbon deposition, from DTA-TG result in figure 2 indicating that the nature of coke deposit may not be the same at different reaction temperature. And figure 3 show the amount of carbon deposit on catalyst react at 500 or 550 degrees Celsius is much higher than any reaction temperature, whereas figure 4 show ethanol conversion is not decreased, suggesting that carbon deposition is not a main problem on cobalt or silicium oxide catalyst for ethanol steam reforming at the high reaction temperature. From TM image in figure 5, at 450 degrees Celsius or lower temperature, catalyst particles are heavily enclosed by coke, and that is encapsulating carbon. Encapsulating carbon results in severe deactivation. At 500 degrees Celsius, the carbon diffuse behind the particle, nucleating the ghost of carbon filament. The filamentous carbon leaves the cobalt particle from the support, and filamentous carbon result in mild deactivation. The figure on the right hand side show characteristics of filamentous carbon and encapsulating carbon. At 700 degrees Celsius, the carbon deposition rarely occurs. For effect of water ethanol molar ratio to carbon deposition. From two research explained that increasing the water ethanol molar ratio result in increased ethanol conversion. Ethylene production decrease because water inhibit dehydration of ethanol, and selectivity of carbon dioxide increase when selectivity of carbon monoxide decrease. This could be related to contribution of water gaseous reaction and carbon gasification with water. From table 1, table 2, and figure 9 indicating that increasing the water ethanol molar ratio result in decrease in the amount of carbon deposit on the catalyst surface. Moreover, from table 2 show carbon deposition was no longer observed during ethanol steam reforming at high temperature. And for conclusion, main deactivation of cobalt on cerium oxide catalyst is
3 minutes
caused
left.
by carbon deposition. The byproduct of ethanol steam reforming lead to the formation of coke, which can in turn induce catalyst deactivation. And the reaction temperature exerts influence on coke formation and its property significantly. At the last, higher water ethanol molar ratio is one of possible strategy to reduce the carbon deposit. This is all of my presentation. Thank you for your attention.
Thank you, Mr. Supakit. And
how many left?
Next is Muhammad.
The last one. Okay, Muhammad, please prepare your slide. And the rest of the referee, if you finish the grading, please upload to course view again.
Hello everyone, can you see
Hello.
my screen? Hello.
Yes, Muhammad, are you ready?
Yes, I'm ready.
Okay, please.
Should we start now or wait for until 11:25?
Yeah, you can start now.
Okay. Okay, hello everyone. My name is Mohammed Freduni. I will present about indium oxide catalyst for direct CO2 hydrogenation. In this presentation, I will focus only on the stability of the catalyst, not on the activity of the catalyst. So my presentation will be in 4 parts. The first, I will go through the introduction. The second part, I will talk about the conventional and the new approach for the methanol formation, methanol production. And in the third part, I will deeply talk about the indium oxide, why this is a good catalyst for direct CO2 hydrogenation, and the problems with this catalyst and the activation reason behind the activation of the indium oxide. And at the end, I will have a brief conclusion. So the first part, first of all, why everyone, especially in the recent years, are focusing on the CO2, while the CO2 is not the only greenhouse gas, but everyone is now focusing on the CO2 management or CO2 hydrogenation. The reason is that CO2 not, as I said, is not the only greenhouse gas, or doesn't have the most adverse effect on the environment. But the problem with the carbon dioxide is the production rate of carbon dioxide. As you can see on the right-hand side, the production rate of carbon dioxide in the United States, compared with other major greenhouse gases, we can see that 80% of the greenhouse gases produced in the United States in 2019 is carbon dioxide. And on the left-hand side, you can see if you want to keep the temperature, raising the temperature of the atmosphere around 2 degrees based on the Paris Climate Agreement, we need to decrease the production of the carbon dioxide. But the problem is that we need energy, and the demand for energy is increasing by the time. So there is a relation between the demand of the energy and the CO2 production, because mostly CO2 is coming from the plants or from energy plants which use hydrocarbon resources. So we need increasing the production of carbon dioxide is no doubt. So now we need to find a way to manage the CO2 or to transform CO2 into like fuel or something that we can use it to produce the energy. and control the emission of the carbon dioxide. The production of the carbon dioxide will be increasing by time. But it is really interesting to hydrogenize carbon dioxide into fuels like methanol or methane, but there are many challenges. The first problem is the hydrogen required for the CO2 hydrogenation. This hydrogen, if it comes from the conventional methods, conventional processes like methane reforming, there will be more production of carbon dioxide. So we need to find a way to produce hydrogen from a carbon dioxide free resource. So this is the first challenge. The second challenge is the stability of carbon dioxide. Carbon dioxide is highly stable. So finding a catalyst and finding the reaction conditions which can activate and stabilize, activate carbon dioxide and stabilize the intermediates is also a challenge. So conventionally or in the industry, ethanol is being synthesized over copper zinc oxide alumina catalyst. This is a metal catalyst, not an oxide catalyst, but the catalyst then is synthesized in the oxide form. So this catalyst needs to be reduced to copper, needs to be, then the activity must be stabilized, and the process of just stabilizing this catalyst in the industry can take up to 3 days, which means we lose a lot of losing time, losing money in the industry. And the other problem with this catalyst is that this catalyst uses hydrogen and carbon monoxide as a feedstock. Carbon dioxide is only added to the inlet stream or added to the feedstock just to increase the reaction rate. But actually carbon monoxide and hydrogen are used for the methanol formation. And then this catalyst is being used for direct CO2 hydrogenation. It shows low selectivity and stability. So this catalyst is not good for direct CO2 hydrogenation. Now, researchers are focusing on direct CO2 hydrogenation, and they are proposing that oxide catalysts are better than metal catalysts. They have higher selectivity, stability, especially stability to temperature for the methanol formation, direct methanol formation from carbon dioxide. Among the many metal oxides being studied, I will only focus on the indium oxide, which has been recently studied a lot.
3 minutes left.
Okay. In this part, you can see the structure of the crystal, and with the indium oxide, with just adjusting the reaction conditions, including temperature, pressure, and space velocity, we can increase the selectivity of the catalyst for methanol and avoid reverse water gas shift reaction. And here we talk about the reaction mechanism as proposed by DFT calculations and supported by experimental research. The oxygen vacancies of indium are actually the active sites for the hydrogenation of the carbon dioxide base. So based on this mechanism, oxygen vacancies can be lost. And if oxygen vacancies are lost, then the catalyst would be deactivated. In this very specific paper that I am reviewing here, they synthesize the TEM to desynthesize the indium oxide with the average particle size of 7 nanometer, and then measure the XRD. The XRD confirms the formation of the indium oxide. Then they studied the XAS in situ, XAS and XRD, and the results are really interesting, as you can see in the F and G figures. In the F, as the time passes and the reaction occurs, the amplitude of the peak of the indium oxide is decreasing and the peaks are becoming wider. And on the graph G, you can see the amplitude of the indium oxide and indium shells also decreasing by the time on a string. So based on the results of the XAS and XRD in situ XAS and XRD, we can derive this information as you can see in the figure on the left. So in the first part of the figure, in the A, you can see that the production rate of the methanol can be divided into 3 regions. First, the activation, then the stabilization, and finally the deactivation. But in the coordination number, in the second graph, you can see the coordination number for indium oxygen and indium is decreasing by time. it means that the indium is being reduced, and that's the reason the catalyst is now active, because now it's producing oxygen vacancy, but is decreasing the coordination number, keeps continuing, so finally the catalyst is deactivated. And you can see the crystallinity of the catalyst at the bottom of this figure. Also, by the time on stream, the crystallinity of the catalyst is decreasing, which is in agree with the XRD graph. So the
1
problem
minute
of
left.
the problem of the deactivation of the catalyst is loss of the crystallinity and finally reducing to indium 0. The interesting thing about this catalyst is that not only the temperature and the reaction medium, but also the beam of the TEM equipment can also cause this problem and can transform the indium from the oxide to amorphous. So in the conclusion, indium oxide is really promising as a good catalyst for the CO2 hydrogenation, but there are some problems, including the stability of the catalyst, losing the oxygen vacancy site, and also transforming from the crystal to amorphous. Thank you for listening.
Okay, thank you, Muhammad.
You're welcome.
And thank you, everyone. So, did you have all the score sheet? If anyone has needs to see the rerun, I will upload the video within tonight, because it will need like 2 hours to process. So for this is the last lecture, the real last lecture. I would like to thank everyone for joining us for the whole semester. And yes, if you have any question, you can post it in my course view. And as I said that there will be no examination for the finals, and this is the real, I mean, the score for your presentation is the score for the finals, and together with the report. So please have, I mean, do your report with good care, I mean, and upload it and recheck that if it's worth the score that you will get for the final. And we still have time for the to upload the report, so you still have a week, I think. What is the deadline again? I think I set it to like next Friday or something. Yeah. So upload to the course view, and we'll see you in maybe some other lectures, seminar, or within the department after the COVID. Okay. So yeah, if you would like to turn on the camera, and yeah, we will dismiss the class. Okay. Is anyone here? Okay. Okay. สวัสดีครับ Okay. Goodbye, everyone. This is the last lecture. Okay. And see you. ผมคือเป็น ET นะไม่มีใครเปิดไมค์เลยนะโอเค
สวัสดีครับ
สวัสดีครับบายบาย
สวัสดีครับ
สวัสดีค่ะอาจารย์
สวัสดีครับ
การ